We are in chapter 5, which is on shear. This is the 39th session overall. Here we discuss some examples involving shear stress. This was the roadmap for the first 4 chapters. When it comes to loading, we have discussed axial loads, torsion and bending. And now we are discussing shear. This is chapter 5, where we are discussing shear. Till now we have looked at the theory of structures with 2 axes of symmetry. In this third session, we look at examples of shear stress for structures with 2 axes of symmetry. After this, we'll discuss unsymmetrical loading. We look at stresses in thin sections. This is the section with the dimensions given, and this is the loading on the beam. We are required to find out the maximum shear stress in section 1.1 as well as the maximum shear stress in the whole section. We plot the shear force diagram for this loading, and we find that the maximum shear force is 14 kN. So we find the shear stress in section 1.1 and the maximum shear stress in the section due to this load. We find out the IZZ of the section. In order to find out the shear stress in section 1.1, we find Q of this shaded portion. So here we have determined Q. Thickness here is 8 mm, but for this shaded portion, we have twice the thickness. So B is taken as 16 mm. Shear stress is found in section 1.1 by taking B as 16 mm, as shown here. The maximum shear stress occurs at the neutral axis, and for determining the maximum shear stress, we take this whole shaded area and find Q. Again, we take twice the thickness as B and find tau max. Here we have another problem with the dimensions shown, and we are required to find out the stress at section 1.1 and the maximum shear stress in the section for this loading. So again we have drawn the shear force diagram, and the maximum shear force is 22.67 kN. So we find the shear stress at section 1.1 and the maximum shear stress for this loading. In this case, the section is not symmetrical, and we find YC first. Once we have YC, we can find out Q11 for this portion. The maximum stress is at the neutral axis, and we can also find Q for this portion. With the position of the neutral axis known, we find out IZZ of the whole section. So we have found out tau 11 and tau max. Here P is the thickness of this section, which is 16 mm. We are given this section along with the dimensions and the shear force acting, and we are required to find out the shear stress at 1.1 and 2.2. Find out IZZ of the whole section. In order to find shear stress in section 1-1, we find out Q for the portion AB. So here we have given Q11. Shear stress is found out by taking B as 12 millimeter, which is the thickness. For section 2-2, we take Q of this portion CD. So this is the Q. Now in this case, the shear stress here and here will be the same. So the shear stress in 2-2 is found by taking B as 2 into 12. We are given a cross section with dimensions and also the shear force acting. We are required to find out the shear stresses from sections 1-1 to section 5-5. To start with, we find the moment of inertia of the whole section. To determine the stresses at all the sections, we find out the corresponding Q. For section 1-1, Q is 0 because this is the free end and also the distance from the neutral axis is 0. To find out the stresses at section Q22, we find Q22. Thus, we find Q of this vertical portion. The area is 50 into 8 and the distance of the centroid is 50 divided by 2. For determining the stresses at section 3-3, we find the corresponding Q. Q33 is of this vertical leg and this horizontal leg. We determine the Q of the vertical and the horizontal leg separately. For the horizontal leg, this distance is 80 millimeter. So we take 8 millimeter on the right side and 4 millimeter on the left side, and we get the dimension as 68 millimeter. To find out stress in section 4-4, the Q has to be taken of this whole portion. We consider the Q of the vertical portions and the horizontal portion separately. For the horizontal portion, the whole length is 160 millimeter, and we take 8 millimeter on either side, and we end up with 144 millimeter. To find stress at section 5-5, we need to take off the cross section. So we need to take all these portions. So we consider Q of these two vertical portions, this horizontal portion, and the portion between 4-4 and 5-5. The length between 4-4 and 5-5 is 50 minus 8, that is 42. Having obtained the Q for all the 5 cases, we can find out the stresses. The thickness is 8 millimeter for all the cases. As in the previous problem, here we have been given a cross section with dimension. The shear force acting is known. We are required to find out the shear stresses from sections 1-1 to section 6-6. To start with, we find out the moment of inertia of this whole cross section. In order to find out the shear stresses, we need Q, or the statical moment of area, for all the 6 sections. Consider section 1-1. We need to take the Q of this vertical portion. Half this length is 46 and the thickness here is 6. So the height of this portion is 40. So here we have found out Q11. Consider section 2.2. We need to find out Q for this vertical portion. We notice that the centroid of this vertical portion will be on the neutral axis. So the distance of the centroid from the neutral axis will be 0. That means Q22 is 0. Now consider section 3.3. We need to find Q for this horizontal portion. Since the Q for this portion is 0. This length is 42 plus half the thickness is 45. So we find Q33. Consider section 4.4. We need to find the Q of this whole portion. But for this portion, the Q is 0. So we need to find out the Q for this horizontal portion and this vertical portion. Here we obtained Q for 4. Now consider section 5.5. The Q will have to be taken for this whole area. Now consider this whole vertical portion. The centroid of this vertical portion coincides with the neutral axis. So the Q of this whole vertical portion is 0. Also, we have earlier found that the Q of this portion is 0. So we need to take the Q of the portion left of this dotted blue line. This length is 45 minus 6, that is 39. So we have found out Q by 5. Consider section 6.6. Then the centroid of this whole portion coincides with the neutral axis, and as such Q is 0. The thickness B is the same in all these cases, and we have found out the stresses from section 1.1 to section 6.6. Here we determine the maximum shear stress for two geometries, a ring and a triangular section. The ring is the cross-section of a pipe. We consider the thickness of this ring as Tm and the radius of the center line as Rm. Then the moment of inertia is given as pi Tm Rm cube, and the area is given as 2 pi Rm into Tm. The maximum shear stress occurs at the neutral axis. To find the shear stress at the neutral axis, we need to find Q for this dark shaded portion. The Q of the dark shaded portion can be found out by first finding the Q of the larger semicircle and then deducting the Q of this smaller semicircle. The centroidal distance is given as 4r divided by 3 pi for a semicircle. The radius for the outer circle is Rm plus Tm divided by 2. So here we have Q for the larger semicircle. It is given as area into centroidal distance. Area is pi r squared by 2 and centroidal distance is 4r by 3 pi. For the inner circle, the radius is Rm minus 2pm divided by 2. So here we have given the Q of the smallest semicircle. The area is pi r squared by 2 and the centroidal distance is 4r by 3 pi. Multiplying and subtracting, we get this expression for Q. So this is the Q of the shaded area. Now the first term in this expression can be written as 4/3 Pm into Rm squared. Multiplying this outer term with the second term within the bracket, we get 2/3 Pm Rm squared. Adding the two up, we get 2 Tm Rm squared. Multiplying the portion outside the bracket with the first term in the bracket, we get Tm cubed divided by 6. Now Tm cubed would be very small, and so we ignore this second term. So Q for the shaded area is given as 2 into Pm Rm squared. Tau is equal to Vq by Ip. Here P is 2 Tm. We substitute Q, I and B in the expression. Tm here cancels out. Cancelling the Rm terms, we get a single Rm in the denominator. So in the denominator, we have 2 pi Tm Rm, which is the area. In the numerator, you have 2V. For a circular portion, shear stress will not be vertical always. Consider a point P. There will be no shear stress perpendicular to the surface. So the direction of the shear stress will be along the tangent to the surface. However, at the neutral axis, shear stress can be considered to act vertically downwards. We now look at the triangular section. For a triangular section, the maximum shear stress does not occur at the neutral axis. The neutral axis is at 2/3 of the height. The maximum shear stress for a triangular case occurs at half the height. Here we'll find the shear stress both at the neutral axis and at half the height. The moment of inertia of a triangular section is given as Bh cubed by 36. In order to find the shear stress at the neutral axis, we need to find the Q of this dark shaded area. Q is area into centroidal distance. Area here is 2/3 P into 2/3 H divided by 2. Centroidal distance is 1/3 of 2/3 H. So we get Q as 4 by 81 Ph square. Tau is equal to Vq by I B dash. B dash here is 2/3 P. Substituting Q, I and B, we get this expression. Cancelling the terms, we get 3 Ph in the denominator and 8 P in the numerator. The area of the triangular section is Ph by 2. So we get the expression of shear stress as 4P by 3A. We'll now find shear stress at height h by 2. We first look at the centroidal distance. Centroidal distance will be 1/3 of h by 2 plus this distance, that is h by 6 plus 2/3 h minus half h. So we get the centroidal distance as h by 3. Area here is p by 2 into h by 2 into half. So we get Q as 1 by 24 bh square. Shear stress is Vq by I B dash. B dash here is P by 2. Substituting Q, I and B, we get the shear stress as 3V by 2A. Since 3 by 2 is greater than 4 by 3, the shear stress at half the height of a triangular section is greater than the shear stress at the neutral axis. We have a hollow section trapezoidal in shape on which a shear force of 60 kN has been applied. We are required to find out the shear stress at A, B, and the maximum shear stress acting on the section. This section has inclined legs, so we will be required to find out the moment of inertia of the inclined portions. We find out the moment of inertia of the inclined portions using the formula for a parallelogram. If this width is b and the height is h, then the moment of inertia of this inclined portion is given as b h cubed by 12. Here h is given, but we are required to find b. We are given this distance and the height, so we can find the length of this inclined portion, which will help us to determine cos alpha. B here is this length x. X cos alpha is 5, which we find as 5.42 millimeter. We have found the centroidal distance about the bottom center line. The moment of the bottom portion about its center line is 0. So we have found the moment of these three portions and divided it by the total area. We next find the moment of inertia of this hollow section. For the inclined portion, we have used this length as b, multiplied it by height cube and divided by 12. Here we have added AD square for the inclined portions. We'll next find the shear stresses at the points A and B. This is the center line, the axis of symmetry. The shear stress at this axis is 0. So to find the shear stress at A, we use the statical moment of this area, which is half of 55 into 5 into this distance. Once we have QA, we can find the shear stress at A. We use the shear force given and the IZZ calculated, and the thickness here is 5 millimeter. So the shear stress at A is found out. To find out the shear stress at B, we consider the statical moment of this area from the axis of symmetry. So it is half of 100 into thickness into 54 minus 31.467. We substitute the same values earlier for B, I, and B to get the shear stress at the point B. We now find the shear stress at the neutral axis. We determine the Q for this portion. So the Q for the horizontal portion is 50 into the thickness into this height, which is 22.53. And for the Q of the inclined portion, we multiply this value by 22.53 is the height, and the distance of the centroid is 22.53 divided by 2. So here we have got the Q related to the neutral axis. The maximum shear stress at the neutral axis will be along a length that is perpendicular to the sides, which is the thickness. So to find the shear stress at the neutral axis, we use 5 as B. Here we have a square hollow section oriented as shown, to which a 45 kN load is applied. We are required to find out the maximum shear stress in the section. The shear flow in the section will be as shown in this diagram. We'll require this distance x of the inclined portion. Thickness is 8 mm and this angle is 45. So x is equal to 8 divided by cos 45 or 11.312 mm. For a square oriented as shown here, the moment of inertia about this axis is given by this expression. Here 108 is the length of the side of the outer square and 92 is the length of the side of the inner square. The shear stress on this axis of symmetry is 0. So to find the shear stress at the neutral axis, we have to consider the statical moment of area of this portion. The vertical distance to the neutral axis is 100 divided by root 2, and the distance of the centroid of this portion is half of that. So the statical moment of area is given as 11.3 multiplied by 100 by root 2 into half of that. With Q known, we find out the shear stress at the neutral axis. As earlier, we take B as the thickness, which is 8 mm.